Hello, today we're going to be looking at piecewise functions, and we're going to be talking about a little bit about graphing piecewise functions just to understand what they are, and then talk about evaluating functions and limits using piecewise functions. So what's a piecewise function? A piecewise defined function sometimes will include the word of defined, sometimes won't. Basically has different rules depending on what x is. So what do we mean by that? So a function really, all it does is assign to each input some output. And usually our functions are nice enough, like f of x equals x squared, that the same rule, the same simple rule works for all x. But our functions don't need to be that nice. Our functions could, maybe it's only x squared sometimes, and somewhere else we define it otherwise. And that's basically what we have here. This function, if x is less than 1, then we're going to evaluate it by doing 2x plus 4. If x equals 1, we'll just say the answer is 3. And if x is greater than 1, then we're going to do negative x minus 3 squared plus 4. So actually, I'm going to bounce around back and forth a little bit. Let's start by just kind of practicing this a little bit. So we're going to have to find some values. I'm going to not do the limits yet. We'll do those later. So if I'm asking what's f of 0, I'm going to look at my piecewise defined function. 0 is less than 1. So I'm going to use this first rule, 2x plus 4, to figure out what it is. So it's going to be 2 times 0 plus 4, which just equals 4. Easy enough. What about f of 1? Hey, when x equals 1, it actually has its own rule. It's just going to equal 3. So that was easy enough. And what's f of 2? Well, when x equals 2, this is x is greater than 1, so we're going to have to use this this last rule. So it's going to be something like negative 2 minus 3 squared plus 4. This is negative 1 squared plus 4, which negative 1 squared is just 1, so this is negative 1 plus 4. That's going to equal 3. Okay, cool. So we were able to evaluate this function at some different points using this piecewise definition. We just looked at, hey, is my input less than 1, equal to 1, or greater than 1? And that told me what rule to use. Now we could also sketch this function, and here we're going to have to remember a little bit about how we graph various functions. So I'm going to give myself about 3, 4, 5, 6, 7, 8. I know that I have something that goes up to at least 6 here, so. Okay, so we're going to draw ourselves a nice graph. And what I'm going to do is I'm going to draw each of these pieces in different colors. So let's start with red for the first piece. When x is less than 1, so I'll draw a little dotted line here to just show that this is going to be something different depending on if it's less than, equal to, or greater than 1. We're going to have the line 2x plus 4. So that is that's a line that's in slope-intercept form, so I know it has a y-intercept of 4, and it has a slope of 2. So we can go down to the left one, up to the right one, and we'll get this line right there. But there's a slight caveat, which is that the function doesn't actually touch this point here. Because at this point, when x equals 1 exactly, we have a different definition for this, right? That definition, so in fact, I'm going to erase this and just draw that really clearly. So we're going to have this little open circle at 6, representing that, hey, we don't actually use this value when x equals 1. Instead, when x equals 1, we're going to use the value 3. Oh, I said I was going to use different colors. Let's use a different color there. Let's call that blue, just representing that's coming from this middle piece. Okay. Now let's do the last piece in green. So let's take a look at this. There's actually some transformations going on here. It looks to me like what we did is we took x squared, and then we did a vertical reflection, and then we went, so that's this negative sign is giving us that vertical reflection. And then we went to the right 3 and up 4. So we're going to take x squared, which looks like this parabola, and I'll draw it a little bit more carefully. We're going to turn it upside down, and then we're going to shift it a little. That's not what up 3 or to the right 3 and up 4 looks like. It's going to look something like that. We're going to just move it up. So let's start by drawing the corner, or the we'll say the minimum of this parabola. I think sometimes we call it the vertex. So we're going to go 1, 2, 3 to the left 3. And actually, you know what? Here's what I'm going to do. I'm going to sketch it negative x squared. I'm going to sketch it small just so we know what we're working with. So it crosses through 0, it goes through -1, -1, and 1, -1, and then it'll also go through 2, -4, 1, 2, 3, 4, and -2, -4. And then it'll kind of keep going like that. So this is what we're going to be transforming. We're just going to be moving it a little bit. So we're going to be moving it, as we said, to the right 3, 1, 2, 3, and up 4, 1, 2, 3, 4. So we're going to have this point here. And then we're going to go this point here from -1, no, or -1, -1 is going to go over 3 and up 4 to here. This point here is going to go over 3, 1, 2, 3. Oh, that's on our line. And then up 4, 1, 2, 3, 4. Remember that we're not actually using this piece on this line, so I'm going to draw a circle there. And then we'll have some similar stuff happening here. And we end up with this parabola that looks sort of like that. So here's my piecewise defined function. For x is less than 1, we have this line. For x equals 1, we just have the point here. And for x is greater than 1, we have this parabola that's been transformed in a few ways. Okay. So this picture is nice, and it could help us do our limit, but usually we're not going to draw a picture first when we do the limit. So I'm just going to pretend that we didn't draw this for a little bit. So put this in your imagination box, because we're not going to use it. I just made it more obvious on the paper. But again, we're just going to not look at it for a little bit. And we'll talk about how we'd usually define or calculate these piecewise limits. So let's talk about the limit as x approaches 1 from the left. Well, maybe we'll use the picture to get some intuition. If I was using the picture, I would look at what's happening to the function just to the left. So we have this piece to the left of x equals 1. And I'd ask, if I look at that piece, what does f of 1 look like? So again, we don't have the picture here, but we can ask the same thing. If I look at the piece that tells me what's happening to the left of 1, that's this first piece. So what would that piece be telling me f of 1 is? So it would be telling me that I should use the rule 2 times. Actually, I'm going to write something. I might not have room to write this, but what we're really going to be doing is we're interested in this piece, 2x plus 4. Because that's the rule that applies for things less than 1. And this is a nice function. We can just plug 1 into that. So we'll just get 2 times 1 plus 4, which equals 6. For this one, we're going to use a similar trick. we're going to look at the rule that tells us about things bigger than 1. That's going to be this last rule. So we'll have the limit as x approaches 1 from the positive direction of negative x minus 3 squared plus 4. And we can plug that in. That's going to give us negative 1 minus 3 squared plus 4. That's going to be negative 2 squared plus 4, which equals 0. And we'll just note that agrees with our picture. As did this, by the way. And then we ask, well, what about the limit as x approaches 1? Well, the general rule here is that in order for this limit to exist, both the one-sided limits need to exist, and they need to equal the same thing. But in this case, they both exist. Limit as x approaches 1 from the negative direction, we get 6. X approaches 1 from the positive direction equals 0, but they're not the same thing. So this limit actually doesn't exist. So we'll write DNE for that, because the limit doesn't exist. So there we go. Just to kind of summarize, when we have a piecewise function, that just means we have different rules for each of the pieces. And we can use those rules to just evaluate the function. We can even use those rules to sketch the function on those different intervals. But then, when it comes to limits, it really boils down to figuring out which of these pieces do I need to use to tell me about the part of the function I'm interested in. So if I'm approaching 1 from the negative direction, I need the piece that tells me about things just less than 1. If I'm approaching 1 from the positive direction, I need the one that tells me about things just bigger than 1. So there we go. There's a little bit about piecewise functions and a quick review of transformations of functions.